Okay, so number 6 deals with accuracy and precision. Now, accuracy refers to how close a value is to the actual or true value, the accepted value. So if you're trying to get the density of something, and you know in a textbook it tells you that the density is 5.0, and you come very, very close to 5.0, then you know you're accurate. If you're not anywhere close, then you're not accurate at all. Precision deals with, if you do it over and over again, are you consistently getting the same measurement? If you're trying to measure the density of something and you know it's supposed to be 5.0, but yet you keep getting 3.2, 3.1, 3.2, 3.3, and you're still in that range, then you must be doing something wrong because you're not accurate, but you are precise. You keep making the same mistake over and over again. So one of the definitions of precision is how reliable a measurement is. Are we doing it over and over again? So if you take these two definitions, you can look at these pictures here. Now, apparently we're shooting for this little circle in the middle. This first picture is not accurate nor precise because the numbers aren't hitting, or the dots aren't hitting the bullseye, and they're all over the place. This one is not accurate, but it is precise. They're missing the mark, but yet they're pretty much predictable. And over here, the best of both worlds, especially in science, you want to hit the mark and you want to do it over and over and over again. So you want to be precise and accurate. So this is what we're shooting for in science. Now, the second definition of precision is the amount of information given in a number. So, for instance, if you have a number 0.12, that's more precise than just 0.1. It gives you more information. 855 is a lot more information than just 800. 800 is, it's somewhere between 0 and 1,000. We're guessing it's about there at the 800 mark. 855 is saying it's somewhere between 850 and 860. We're guessing it's about halfway in between the 850 and the 860. So this range is a lot more, is a lot smaller, and we know a lot more information and a lot more confidence than this big range. We're just guessing it's about 800, but over here we can narrow down that range more. And then it says, devise a scenario where measurements are precise but not accurate. Imagine we had a true mass of an apple at 5.80 kilograms. The apple's mass on a scale 4 times, and the scale read 4.2, 4.1, 4.2, 4.21, and so forth. So if we keep getting the same numbers over and over again, we consider them precise, but we're not hitting our mark. We're not getting the true mass, so it's not accurate. Now the next part says, explain how the Atlantic-Pacific rule can be used to determine the correct number of sig figs. Now what you need to do is imagine your number is the United States. And hopefully you know that this is the Atlantic side and this is the Pacific side. If the decimal point is absent, so if you look at a number like 100 and you don't see the decimal point, then you're going to come in from the Atlantic Ocean side because it's absent. So you're going to look at the number this way. If the decimal point is present, let's say the decimal point's there or it's even 100.0, then you're going to come in from the Pacific Ocean side into the number. The next rule is start counting with the first non-zero digit. So if you come in from the Atlantic side, you hit a 0, you can't count yet until you get to this 1. And the last rule is count till you run out of things to count. So you hit the 1, you start counting, and you also end counting. You can't count anymore, so there's only one sig fig. One number that means something important to us. If you go this way, right away you run into a number. You hit the 1. And you count till you run out of things to count. So 1, 2, 3, 4. There's 4 sig figs there. So there's 4 bits of information. 100.0 tells us a lot more information than 100. Okay, let's use that to figure out how many sig figs are in the following numbers. So pretend each one of these numbers is the United States. This one, decimal point's present, so I come in from the Pacific side. None of the zeros count till I hit the 3, and then the 3 counts. This way I come in from the Atlantic Ocean side, none of the zeros count. 1, 2. 2 sig figs. Whenever you see scientific notation, ignore it. Pretend it's not even there. Just count whatever you see. 1.45, 3 sig figs. And this one, decimal point's present, so I start on this side, Pacific Ocean side. 7, 0, 1, 1, 2. So there's 5 significant figures here. Number 9. What rule do you follow when determining where to round when you multiply or divide? Now there's 2 sets of rules, and we're going to go over these rules, which is for multiplication and division, and then we're going to go over the set of rules, which is for addition and subtraction. So let's do multiplication and division first. Now this one, you have to understand how to count sig figs, because then you have to figure out which one's got the least total number of sig figs, and you're going to have your answer, or you're going to round your answer so it has the same amount. So this one, it's got 4 sig figs. Pacific Ocean side, 1, 2, 3, 4. This one, Pacific Ocean side, 1, 2. So we got 4 sig figs versus 2. 2 is the least amount. That's our worst measurement. So we're going to go with 2 sig figs in our answer. So you're going to multiply these guys. The calculator spits out 360. Now mathematically that's correct. But unless you have this setting on your calculator, this significant figure setting, the calculator has no idea about sig figs. So you need to round this so there's 2 sig figs. So you look and say, is the decimal point absent or present? It's absent, so we start counting, and 1, 2, we're all set. 360 has got 2 sig figs. Now what if this was 8.00, and suddenly there were 3 sig figs? This has only got 2, so you need to make it have 3. Now there's 2 ways to accomplish this. The first thing is that you can write 3 sig 0 and put a little decimal point at the end. If you put a decimal point there, then suddenly it changes the game. You're not coming in from the Pacific Ocean side anymore. Now you're coming in from the, you're not coming in from the Atlantic Ocean side. Now you're coming in from the Pacific Ocean side. And you start counting 1, 2, 3, and now you've got 3 sig figs. The other thing you could do is put it in scientific notation. Make it 3.60 times 10 to the 1, 2, 10 to the second. And that'll also have 3 sig figs. So you can either add a decimal point at the end, or you could actually put it in scientific notation. Now this B one here, you got 20, no decimal point, so you come in from the Atlantic Ocean side, 0 doesn't count, the 1's the only one that counts. So 1 sig fig versus, they all count, the 3, the 3, the 4, 3 of them there. 1 versus 3, so my answer is going to have 1. So the calculator is going to shoot out this crazy answer, 598.023952, and you have to interpret that mess. You've got to keep 1 sig fig, so you're going to keep the highest place value. That 5 is, that place value rather, is going to stay the thousandths place. Now that 5 could stay a 5 or it could round up. Before we lop off the rest of this mess, we have to see what that 9 does to the 5. That 9 is higher than 5, so it rounds this 5 up to a 6. Now if you just wrote 6, you're losing the whole meaning of the number. It's got to be 6, and then you're going to hold places, 0, 0, 0. Don't put a decimal, because you want to go right through these guys to get to the 6 and have 1 sig fig. So you want the decimal to be absent, so you can come in from the Atlantic Ocean side. So you could either write 6,000 like that, or you could write 6 times 10 to the 1, 2, 3. And the decimal point's absent also, and we just have 1 sig fig. So there's a couple of different ways you could do these problems. Now, when you add and subtract, I've said before that you could probably walk into a second grade classroom and teach the kids this. This isn't hard because all you have to do is recognize where the decimal point is and line them up. Here's the 45.00. You're adding 8.0 to it. You're going to say to yourself, I have nothing in the hundredths spot, but I do have values in the tenths for both of them. So my answer is going to have a value in the tenths. So when you do out the math, even though the calculator shows 53, you need to record 53.0. You need to match your weakest number, which is in the tenth spot. Over here, we got nothing in the tenths, no decimals whatsoever. So you're going to match up 20 minus 0.34. When you do the math, you end up with 19.66. And then, because this is your weakest number, your most vague number, you're actually not going to keep any of these guys either. Before you lop off the 66, you're going to round that, or use a 6 to round the 9 up, and you're going to make it 20. So this is such an insignificant amount compared to 20, since 20 is such a vague amount, we can't even consider this. So your answer, unfortunately, ends up 20 again. All right, let's go through some measuring now. Okay, what I like to tell you when you're measuring here is to find the place value before and the place value after the mark that you're supposed to be measuring. So this big line is 12, this big line's 13. These little guys are the tenth spot. So this line here is 12.3. This line here is 12.4. So you know it's at least 12.3. You know it's not 12.4. And you're going to take a guess. How far in between these two values is it? And it looks to me like it's a little shy of the hundredths, or the halfway mark. So I'm going to write maybe 12.33. If you decided it's 12.34, that's okay. If you decide it's 12.32, that's fine. As long as you definitely have, everybody should have 12.3, and then a guess that's a little bit less than halfway. Let's look at B. We know it's at least 30. We know it's not quite 31. In fact, it's nowhere near 31. I actually think it's right on the line. So I'm going to say it's 0/10 of the way between 30 and 31. So I'm going to write down 30.0. Let's see if I can zoom in a little bit. Okay, a little bit better. So now the next one. Here is 28, and here's 29. It's somewhere between 28 and 29. I think it's about halfway there. So I'm going to say it's about 28.5. And this one is 15, and this line's 16, and I think it's 0/10 of the way between the two. So it's 15.0. And then finally, this is 4, this is 5, this is 4.5, and the next line up is 4.6. I think it's 0/10 of the way between the 4.5 and the 4.6, so I say it's 4.50. Saying 4.50 is different than saying 4.5. If I say it's 4.50, I see the 4.5 line. I see the 4.6 line. I know with confidence it's 0/10 of the way, or I'm guessing at least, it's 0/10 of the way between those two values. If I just say, yeah, it's 4.5, I'm saying here's 4, here's 5, I'm guessing it's about halfway in between. We know it's halfway in between. We see the 0.5 line. That's not an issue. We even see the 0.6 line. What we're doing now is narrowing it down in this little tiny range. So it does make a difference adding that extra 0 or not. It gives you more information, the number's more precise. Okay, so what we need to do now is know our prefixes. Basically for this test you just have to know 4 main prefixes. You should know centi is 100 times smaller than the base. So let's take a look at this picture. If you look at this little ruler here, this is a meter stick. These are centimeters, between the 5 and the 6. Between the 7 and the 8. Those are centimeters. It's the width of your fingernail. Millimeters are the distance, basically, of the thickness of a dime. There's 1,000 little millimeters in 1 meter. It's 1,000 times smaller than the big meter. Kilo, if you put 1,000 of these meters together, meter after meter after meter after meter and so forth, you got 1,000 of them, that's your kilometer. And deci is, see where this 10 is? If you could trace that all the way back to the 0, that's a decimeter, a tenth. So if you took your whole ruler and divided it into 10 sections, each one is a decimeter. So know your prefixes, know what they mean, know if they're bigger than the base unit or smaller than the base unit, and then be able to do conversions. So if I said which is bigger, 3.45 kilometers or 34,500 meters, you should be able to do some comparisons using dimensional analysis. Now, I gave you a hint. I said set up a dimensional analysis problem to convert both to the same units. I don't care which unit you pick. Eeny, meeny, miny, moe, pick your favorite unit. I'll stick with the base unit. I'll stick with meters. I'm going to convert 3.45 kilometers to meters. So I'm going to put that there, kilometers on the bottom, meters on top. I know that there's 1,000 meters in 1 kilometer. So this times 1,000 divided by 1 equals 3,450. So that many meters in this original sample here. And then you can compare, because now we have meters and meters, and it's a fair comparison. So which is larger? This one. This one. You got meters and millimeters. So I'm going to convert, let's go millimeters to meters. 340,000 millimeters. I'm going to put millimeters on the bottom, so I get rid of them. I'm going to put meters on top. I know that 1 meter contains 1,000 little millimeters. So I'm going to have to move my decimal over 3 times, and you end up with 340 meters. Next one, kiloliters and milliliters. Let's go from the milliliters up to kiloliters. Let's see what we got here. 930,830,000 milliliters. Now the first thing you have to do is get rid of milliliters. So there's 1,000 milliliters in 1 liter. Then you need to put liters on the bottom to get the kiloliters on top. You know 1,000 liters is in 1 kiloliter. So milliliters cancels, liters cancel. You're basically dividing by 6 zeros, so your decimal point's going to end up there. So it's 930 kiloliters. And then you can compare the two, which is bigger, this one. So your original milliliter sample is actually bigger than this one. Finally, centimeters and millimeters. You've got 965 centimeters. You know that 1 centimeter, one little fingernail, contains 10 millimeters. So it ends up getting a power of 10 bigger, 9650, which is the exact same thing, so they're actually equal.